Hello, everyone, and welcome to the Advanced Methods webinar series. My name is Anne Greenwood, and it's my pleasure to introduce our presenter today. Mr. Resnick will be speaking on record linkage methodology under the Fellegi-Sunter paradigm with extensions. By way of introduction, Mr. Dean Resnick is a principal data scientist with NORC at the University of Chicago. He has been working on data analysis and statistical programming for over several decades. Most of this work has focused on using survey and administrative data for policy analysts, often in healthcare domain. For more than 10 years, he has worked with the U.S. Census Bureau and the administrative record area. Here, he became familiar with record linkage, where it was being used to link very large surveys, enumerations, and administrative record files. During this period, he developed a SAS-based record linkage module for high-volume linkages that is still being used at the Bureau today. At NORC, much of his work is focused on record linkage, and he has developed, in collaboration with colleagues, a new SAS-based record linkage package that incorporates the EM algorithm and several enhanced strategies for improving the quality of record linkage analysis. So welcome, Mr. Resnick. Thank you for joining us and presenting today. Thanks, everyone, for joining us. So without further ado, I'll pass it over to you, Dean.
Well, thank you, Anne. Thank you all for coming to this talk. So let me move to the first slide. I want to give an overview of record linkage in general before I get down to specifics of Fellegi-Sunter and the enhancements that we want to talk about today. So record linkage can be understood in the broader context of data fusion. And I do have the subnote here, which says that it usually implies uncertainty of entity identification. So in certain situations, you'll have files which are nicely prepared and you have a common unique linking key. And in that case, whether or not you're doing record linkage depends on who's ever calling it that's definition of the topic. But for myself, I think that there has to be a level of uncertainty about the identity in order for me to want to call it record linkage. And there are also other terms that are used which are related. So you see deduplication, which is also known as entity resolution, and is more or less the equivalent to linking a file back to itself. And record linkage or deduplication and deresolution can be used for person-level data, organization-level data, address records, and potentially other types of data elements, which I'm not bringing to mind right here. And at NORC, which is where I work, we use multiple linkage strategies, including the use of machine learning techniques. But for this talk, I am going to focus on the use of the Fellegi-Sunter model. And this is a model developed, well, it's a little bit confusing. The actual methods that are incorporated in this model were developed before the seminal paper written by Fellegi and Alan Sunter in 1969 method, I believe, had been proposed by someone named Newcomb. And what Fellegi and Sunter did is they demonstrated mathematically that under certain assumptions, this strategy produces the optimal method of distinguishing matches from non-matches. So I am going to focus on the Fellegi-Sunter, not trying to say that other methods aren't out there and are valuable. Particularly of interest is that there are Bayesian methods, which are currently, there's a lot of work on Bayesian methods, which use a much fuller model. One advantage of the Fellegi-Sunter, at least currently, is that it's simpler and it scales better to large data files than these more elaborate strategies. But depending on the data, you may want to use one of those instead. And so let me talk about what the Fellegi-Sunter model entails. Trying not to get overly technical with this discussion, but essentially what you should be thinking about is, and most of my examples are going to be talking about person level record linkage, is that you have two files and you want to determine which records are matches. So there are pairs where the record from file A and the record from file B represent the same person. That would be called a match. And there would be pairs which you evaluate which do not represent the same person, and those would be called non-matches. And just to try to get the terminology right, what you're doing with the linkage process is you're inferring the match status by a set of pairs which you're going to call links. So in order to assess whether a pair should be linked or not, that is inferred to be a match or not, you're going to use the identification variables which are common across the two files that are being linked. And these would be, for example, first name, year of birth. They could be geography fields. They could be other characteristics of the person. But again, these are going to be fields which are more or less in common on the two files that are being linked to each other. And so for each of these identifiers, you are going to have an agreement weight, which we represent with AW, and a disagreement weight, DW. We'll talk a little bit about how those are estimated later on in the talk. But once you have these, then you're going to go through each of the identifiers, and if the identifiers agree, then you're going to add to the total pair weight the agreement weight for that particular variable. For first name, they agree, you add the agreement weight for first name. Then you go to last name. If the last names disagree, then you're going to apply the disagreement weight. So you're going to go across all of those identifiers, you're going to add them up, and the total of them is called the pair weight. And so the pair weight is essentially what is going to be used to determine whether you want to link the pair or keep the pair unlinked. And so the Fellegi-Sunter theory shows that for optimal discrimination, that you want to set the agreement weight as being equal to the log of the M probability and the U probability, and you also see the formula for the disagreement weight. So I just skipped. The M probability is the probability of agreement given that we have a matched pair. So for example, what is the probability that first name will agree if I have two records that represent the same person? Well, generally we expect that probability to be pretty high. It's the same person, so why wouldn't they have the same name? Well, there could be differences, there could be misspellings. Someone could have used a middle name instead of a first name, or they could have decided they want to be called something different than what they had been called in the past. There are various types of reasons why they wouldn't be in agreement. Same thing, for the date of birth fields. So you're going to have year, month, and day of birth. The year may disagree, usually just has to do with a transcription error, would cause them to not agree if they represent the same person. On the other hand, there is a U probability, which is the probability that two records that do not represent the same individual agree on a field. So that's kind of what I would call spurious agreement. What's the probability that two people will both be named John, even though they're not the same person? Well, John's a pretty common name, so it might happen 1% of the time. For less common names, it will be much rarer. So then the question arises, how do you estimate these probabilities so that you can then compute the agreement weight and the disagreement weight? And there are several methods which I'm showing here. One is a gold standard, is you have some data set which you consider to be reflective of the data that you're working with. And you could say, I know which are the matched pairs, and among those matched pairs, how many times does first name agree, or I should say, what proportion of times does first name agree? And the disagreement weight is actually easier to compute. You could just take random pairs and you can essentially say how often is it that they match up. I'm a little oversimplifying, because if the percentage of matched pairs among the full set of pairs is large, then the disagreement weight is also, if you're not careful, you're going to end up incorporating the true matches into that calculation. So you might want to be careful and only include the pairs that you know are definitely not representing the same person. So the remainder of the talk is going to discuss various strategies that we have been working with when we do our linkages. A lot of our linkage work is done for the National Center for Health Statistics under CDC here in the United States. So I'll just go through these each to show how they help improve the quality of results that come from the record linkage process. I don't know if it's useful for me to just walk through these. I think I'll just let you read through them, and then we'll go through them one by one. Are there any questions up to this point?
I don't see any questions at the moment, Dean, so I'll let you know if there's anything that comes up. Thanks.
Okay, great. Okay, so the first one is the most basic, which is editing and parsing, to try to make the records and the fields for those records as similar as possible on the two files which are being compared. And so among the steps we would use here would be removing punctuation, trying to get everything as all capitals, or they could all be all lowercase, either way. Consistent use of hyphenation, removing diacritical marks and apostrophes. In some cases, you may be dealing with names which have letters that are not part of the standard English set. And in that case, it often will be advantageous to try to equate them with standard English letters. Of course, I'm being biased because I do all my work in English. If you were working in another language, of course, you would have to use that as what you want to make everything consistently fall under. And then it's also important to set invalid values to missing, because what I didn't explain in the previous slide is that if, when you're doing the comparison of first name for one of the files, you don't actually have a first name, or both of them you don't have a first name, then you wouldn't actually apply an agreement weight or a disagreement weight. You would just make the variable weight set to 0. So it is very important to know in which cases you have a missing value, which can be recognized by the linkage software that you're using. There's also value in parsing when you're dealing with names which have multiple parts, whether they're separated by space or a hyphen. And we look at creating different variants, sometimes flipping the order, like for Asian names, or just looking maybe at the second name and trying it as a first name. And we also make use of nickname tables, which we develop. And my suggestion here is that they should be developed parsimoniously. So, for example, you don't need to have nicknames which can be identified through general string comparison. So, Rob and Robert, they're probably going to be, when you're using a good string comparison tool, they will show to be essentially equivalent. So you don't necessarily have to use every possible nickname, but only those which wouldn't be obvious to string comparison routine that is embedded in your process. I sort of alluded to the use of frequency-based weights, and these are particularly useful for names. And here I give an example: Solfa-Gary, Jones. They have, the rare names are much more indicative of match status than the common names, and even more so for first names. Some first names are very common, and so the fact that you agree for David or John has much less value than if you agree on an unusual name. And so we do make use of these frequency-based weights. Essentially, the frequency-based weight corresponds to the U probability in the Fellegi-Sunter model, which is what is the probability that the name field agrees given that the records don't represent the same person. And often these can be developed from a tabulation within a single file, the name frequencies, that is. So this is one. Hierarchical identification variables is something, I'm not clear how widely this is used outside of NORC, but one thing that we have been working with is how do you deal with a situation where one variable's identity is nested within another. And so an example of this, and this is, I'll try to make a conversion for the Canadian equivalent. The zip code, I guess, is what is called the postal code nested within state agreement, which would be the province. So clearly, if the postal code agrees, then I assume that the province is also going to agree. And so from the point of view of the Fellegi-Sunter model, which works best when the variable agreement patterns are independence, this can cause problems to the way that the model is scored. And that's why we make use of the hierarchical analysis. So what we would do here is, first, we would look to see, do the records agree on the province or state? And only if they agree, do we then check to see if the zip code or the postal code agrees. So that would raise the question, well, why are you using both zip and state? Why can't you just use zip code or postal code? And the answer would be because generally there are going to be cases when you don't have a postal code. So you do want to give credit for the fact that the province agrees or the state agrees, even when the postal or the zip code is not available. And the easy way to implement this is by setting the nested variable to missing unless the higher level variable, the province, agrees. And in terms of estimating the weights for these, essentially this is done with the expectation maximization algorithm, which we will talk about a little further on, which is a method of estimating the M and U probabilities and the agreement and disagreement weights when you don't have a gold standard training file to estimate them from. And so this will work just fine using the expectation maximization algorithm. Now, this gets extended, and this is, I alluded to this earlier for name comparisons, is that clearly there are a lot of reasons why one recordation of a name may not agree with another recordation of the same person's name. They can be misspellings, typos, abbreviations, shortenings, and so forth. And in order to perform a richer analysis than just saying, oh, they completely agree, or they don't agree at all, so completely bivariate agreement status, what we make use of is some way of evaluating how similar they are. So full agreement, completely all the letters the same, would generally be like a 1 on that scale. And maybe if they have no letters at all in common, then they would be a 0. But if they're somewhere in between, then they will get an in-between score. If you compare Dave to David, for example, that may rate a score of, I don't know, 0.9, for example. And so there are various types of tools for making these string comparisons. And the one that we have been using most commonly is developed by Matt Jarreau and Bill Winkler of the US Census Bureau, called the Jarreau-Winkler similarity measure. And it works just the way I described. Obviously, I'm not going to talk about exactly how it comes up with the similarity. The code for doing this is actually in the public domain, but if you didn't have access to the Jarreau-Winkler score, there are other tools for doing similarity. And there are also other encodings that can be used to try to render these names in terms of how they sound rather than based on just how the letters occur. But going back to the use of Jarreau-Winkler and also incorporating what we talked about for the hierarchical comparisons, the way that we handle it is we say, okay, we're comparing two names, and the first level of analysis is, do they have a Jarreau-Winkler similarity greater than 0.85? And if it's yes, then there's going to be an agreement weight applied for the 0.85 level. And if no, then they'll get the disagreement weight. Now, if they disagree at that 0.85 level, you're done with the analysis of the comparison of these names. But if they do agree at the 85% level or 0.85 level, then you're going to go further and say, well, do they now agree at the 90% level? So in this case, the M probability, the probability that of meeting the standard, is conditional on the fact that you already know that they were rated above the 0.85 level. And there'll be an M and a U probability associated with these, and which then allow you to calculate agreement and disagreement weights. And again, you will apply an additional weight, which is the agreement weight if they agree at the 90% level. So you'll proceed in this way through all the levels. And in terms of the levels that I'm showing here, 0.85, 0.90, those can be set flexibly. They don't have to be the ones that I'm showing here. I think there is, for Jarreau-Winkler, 0.80 can sometimes be indicative of similarity. So you may actually want to go lower than the 0.85 level as being the base level. But again, this is a way that you can come up with an agreement weight, disagreement weight, let's just say a variable weight as a whole, which incorporates how similar they are in a way which rigorously follows the assumptions of the Fellegi-Sunter model. So this is what we suggest. You see at the bottom of the slide, we have a reference to a paper where we discuss this in more detail. Now, for this, I said you could use Soundex or Nisus patterns in addition. So if you were to use Soundex or Nisus, you could either just say, well, they have exactly the same Soundex, or you could say they have a similar Soundex and come up with levels for the Soundex rather than for the actual characters. Now, this is talking about optimized blocking strategies. I didn't in the outset talk about what is a blocking strategy in the first place, so I guess I really have to lay that out before you're going to understand how to optimize them. And so if you had two files which had 1 million records each on them, then the most rigorous analysis would be looking at all possible pairs between those two data sets. So for each of the records on file A, you'd have to compare them to all 1 million records on file B. And then you're going to have to do that for all 1 million records on file A. So you're going to end up with 1 trillion comparisons. That's great if you have the machine resources to do it efficiently and quickly. In many cases, you will not. And so the technique, which is usually used to get around this, is called blocking. And you define your blocks, and you would often do it the way I'm showing in the example. So you could use the first name, the initial, and the last name initial to set up blocks. And then you're only going to compare people who have the same initials, the records within them that agree. And so that greatly reduces the number of pairs that have to be analyzed to try to find the matches. Now, what I do say here in the third sub bullet is that clearly when you set up a blocking strategy, you're going to eliminate the possibility that two people or two records for the same person, which for some reason did not get recorded with the same initials, get compared to each other. So you'll miss that match. And to get around that, you're usually going to do multiple blocking passes. And then you're going to combine the results of multiple blocking passes and select the best link among them. So then the question is, well, there's a lot of ways you can set up the multiple blocking passes. How can you do it in a way which is effective? And there is a trade-off between the completeness ratio, which is the percentage of true matches which are found, and the reduction ratio, which is the percentage of pairs not analyzed. Now, the reduction ratio, the only importance of that is that you're trying to reduce the workload for your machine, how many pairs it has to process. So the true measure of quality of the linkage is the completeness ratio. But in order to get this to run in a reasonable amount of time, you have to also be concerned about the reduction ratio. And you're trying to find some kind of optimal trade-off between the two of these. And so based on work which was done not by us, we have incorporated what's called the sequential coverage algorithm, which is an algorithm that I don't want to say optimizes is a little bit strong. It's not necessarily optimal, but it's much better than you would get just trying to guess on your own. And this is a way of trying to figure out how many blocking passes you need and what should be the keys. And when I say key, the initial first and last name would be one key. And then a key for another blocking pass could be the date of birth, the month, day, and year taken together. And there are any number of ways you could define a key. So this is a way of trying to figure out which keys you want to use on all your blocking passes so that you have a practical workload and yet you don't lose too many of the true matches from your final link set. So the strategy for doing this is described in this paper, which is referenced here. So you've gone through and you've done your linkage and you want to say, well, how good is it? It's pretty much a an ongoing question in record linkage. How do you know how good are your results? Probably the easiest way is using a gold standard. So for some linkages that we've done, we've actually have, at least for some of the records in the data files, a social security number, SSN. That's an individual identifier. I assume there's a Canadian equivalent. You can use those records. You actually run them through your linkage process and see how many records which have the same SSN end up being returned as links. And that would help you determine what is your, well, the percentage that don't get returned would tell you your type 2 error rate. And at the same time, you could say how many of the links that are made end up with the social security numbers not agreeing, and that would be your type 1 error rate. So that's great in the case where you have something like that can be used to do the comparison. But of course, the question also is whether the records that have the identifier have the same characteristics as the remaining records. So even though if you're fortunate to have a gold standard, it may lead you to estimates which are biased one way or another. So another possible strategy for estimating error, which I'll term a model-based strategy, is going back to the math of the Fellegi-Sunter theory, and you can actually estimate a match probability. And then the type 1 error, let me just say a little bit more about match probability, which is shown as P match. So what that is I've evaluated a pair of records, one record from file A paired to one record in file B. And I think, well, they probably represent the same person, but probably is not very exact. So you want to assign a probability and say, well, there's like a 95% chance that they actually represent the same person. So for that record, if you think about all the records which have 95%, well, then the probability of making a type 1 error is 5%. You just add up all the differences between 1 and that probability, and that would give you your estimate of type 1 error for the full linkage. And the type 2 error is shown with the formula on the third bullet under model-based strategies. So this is a method, and we've tested it, comparing it to gold standard, and it often works very well. There are situations, if you have model breakdown or some of the assumptions that come under Fellegi-Sunter are not met, then these model-based probabilities may not be good, and then your type 1 and type 2 error may not be very good. So in order to use these, you would really want to try to verify that the assumptions going into the model, basically that the agreement patterns are independent, are being met in order to have confidence that the model-based estimates are giving you reasonable values. Now, a third strategy, which I left off of the slide, which is often used, I think Stats Canada, I know they use it at least sometimes, is they just go through the links and they have a person review a sample of them and say whether they think that they actually represent the same person or not. And they just tally them up. How many times do they think they're not the same person? And then they get an estimate of type 1 error. That, in one sense, that's kind of the easiest way to understand. On the other hand, in some cases, it's really hard for someone looking at the records to know, especially if they have common names, first and last names, you really don't always know whether they are the same person. And so that method, we'll say clerical review, is not always a very reliable strategy for estimating error. So I would prefer the model-based strategy as long as the model assumptions can be validated. I think it's a viable strategy, assuming that you don't have a gold standard that can be used. So the next enhancement, if I can call it that, is determination of a cutoff. And that could be done either based on the pair weight itself, or it can be done based on the probability of match. So for example, if I use the probability of match, I'll say I'm going to keep any pair with where the probability of being a match is greater than 0.90 or 90%. How do you determine what level to set? Well, it really depends on how those links are going to be used. So when we're working at NCHS, if you were trying to compute death rates, for example, then if you were conservative and you only kept the links that you were certain, and here, like, just think of one of the files being linked as a source of whether the person is dead or not, then if you're conservative about which records to link, then your death rates are going to be underestimated. So that would be a problem for that kind of analysis. On the other hand, if you're trying to understand something about the probability that a person has a disease given, some other characteristic, it may be the case that it's not really that much affected by the fact. You might actually get better estimates by only keeping the matches that you're very confident of, especially you're building a regression model. You use the ones that you're most confident of, and it should give you a good result. So at least according to my knowledge of the literature, there's not that much of work that's been done on trying to figure out how to optimally set those. So I guess you're just going to have to go in, kind of think, what is important? Do you want to get all possible matches or only the ones that you are most confident of? What of those is going to give you the best resulting analysis? One strategy that we used is trying to estimate the type 1 and type 2 error rates, and then finding the cutoff, which minimizes the total of the two types of errors. That seemed good in theory, but one practical problem is sometimes fairly similar analyses can end up with different cutoff rates, and that may be hard for the people who are using the data to understand. And then the last bullet, I know that work has been done which demonstrates that if you do have a reliable match probability, that you can actually weight by that match probability for a regression analysis to get the most accurate estimates of the parameters. So in that case, of course, you wouldn't actually need a rigid cutoff. You would just be, the low probabilities would just be down weighted. So treatment of sex, gender, the first thing I want to point out about this is that the Fellegi-Sunter model, at least the way that the agreement weights and disagreement weights are supposed to be added to each other, is based on the assumption that the agreement patterns are independent. And for sex or gender and first name, clearly the agreement statuses are not independent, but are instead highly dependent. So if I agree on first name, well, because most names are mostly linked to one sex or another, there's a very high likelihood of agreement on the sex and gender field. The other thing is, it's not really that useful, sex or gender, for determining whether something, two pairs of records are a match. because obviously there's generally close to a 50% chance that you're going to be right, just by spurious agreements. And the other thing to think about is that for last name agreement rates for true matches, so I have two records for the same person. Well, for men, generally the probability of agreeing on last name is much higher than for women, because women often change their names when they get married. So that means that well, I'm going to get to the recommendations. My recommendation is do not use sex, gender as a comparison variable for scoring, evaluating whether a pair should be linked or not. But rather than doing that, conduct separate linkage passes for males and females. In cases where sex or gender is non-binary or it's a missing value, then I would actually create duplicate records for that person and run them through both the male and female passes. You could, of course, come up with a third category for people who are neither male nor female, but a lot of these statuses are, well, I will say that they might be unstable. So I think it's actually more effective to run them through both a male and a female pass rather than creating a third pass for those who are neither male nor female. But depending on, what you're seeing in your files, you could consider that as well. And then software, there's a lot of record linkage packages out there. I will just say at the beginning of the talk, I did talk about Bayesian record linkage. And one of the issues with Bayesian record linkage is that, as far as I'm aware of, there aren't that many existing software options for doing this, which is one reason to favor something more standard like what I'm presenting here under Fellegi-Sunter. So for larger projects, we have relied on custom coding, and mainly because I've been working in SAS for a long time, the custom coding would be in SAS, but it may seem SAS is not the perfect language for this, but we, in order to have greater efficiency for small projects, we've also developed generalized SAS code in a package which we call NorcLink. Of course, again, it's also written in SAS, running on SAS datasets. It performs the EM algorithm. I realize here that I never really gave a good description of the EM algorithm, other than it's a machine learning strategy. E and M refer to expectation maximization. It's a method to use untrained data to estimate parameters. I'm not going to go into the details of how it works. It can be very effective. The software estimates match probability for each link. What is the probability? It is a true match. It does use Giro-Winkler string comparisons for names. It includes nickname substitutions. Name frequencies are taken into account, and we do hierarchical weighting for names, and also some other variables. We do some hierarchical analysis of them. So those are the types of enhancements that we've developed. And here I've given some of the references you can look up. The hierarchical comparisons, I'm currently working on a paper with some collaborators. I know with the training data, I've actually seen that there are cases where if you have variables which are truly hierarchical, but they're not treated that way, that you could actually get pretty poor linkage results. So hopefully that paper will be developed and at some point published. But I do think that it is something which is important to think about when you're setting up your linkages. So, Anne, that's what I have. I'm very happy to take questions.
Great. Thanks very much, Dean, for an excellent presentation. We do have a few questions here, so I'll just start with the first one. The Match IMS linkage program and many state cancer registries require strong matches on SSN, if present, or an address. What impact does this constraint have on false non-match error rates? And how do you handle addressing matching?
So I guess I'm trying to understand it. So, I mean, first of all, if you were only going to accept links if the social security numbers agree, then clearly you can set yourself up for problems. You know, people who either don't have social security numbers or for some reason they don't remember their social security numbers, or they could be people who don't want to share their social security numbers with whoever compiled the data, that those people could be a fair bit different than the people for whom you do have social security numbers. So if you, I'm not sure this is the right interpretation of the question. So clearly, if you were only going to accept links where there was social security number agreement, then you're going to lose general applicability of the results that get used from the linked data to those people for whom you have high quality social security numbers. In terms of error rates, I will say that your type 1 error is going to be very low. You're essentially, the chance of calling something a link and them not actually being a link is going to be quite low. The type 2 error is going to be quite high, is the total number of true matches which remain on link could be quite high if you were dependent on having social security number agreement. So that's how it shakes out. For some analyses, maybe it's okay, but for others, it might not be so good.
Okay, thank you. Next question. We find it necessary to weight the type 1 and type 2 error estimates to take into account the cost of those errors in terms of bias or risk. Do you know of guidelines for different types of studies?
I do not know. I do know, I know, for example, Parthil Lahiri at University of Maryland has done work on incorporating the confidence levels of the match into the analysis. So that would be something to look at. I know also, I believe Fritz Sheeran and Bill Winkler a long time ago wrote up some analysis which relates to this. Fritz worked at NORC and Bill worked at U.S. Census Bureau. So yeah, so those are some places you might look, but I don't really have any better guidance than that.
Okay, thank you. I don't know if there's any other questions. I don't see any at the moment. I'd just really like to thank you, Dean, for presenting today and sharing your work. Just in terms of moving forward, I know you mentioned you have a new SAS, NortLink, I guess.
NortLink,
yeah, that you're using. Do you see doing more, like developing it further with more machine learning techniques in the future, or you think you're at a point where it's fairly stable, or?
No, I definitely would like to continue to develop it. One advantage for us is because, you know, we have the source code, we can pretty much add features to it on the fly, which has proved valuable. One of the things I left off is that we also have developed an organizational name comparison. So that can be kind of tricky. Trying to compare the names of two organizations is actually much different than comparing people's names, because a lot of the same words, tokens get reused. So what we try to do is we try to weight each token's agreement by the rareness of the token. So we were able to incorporate that into our process for projects that required it. So no, I hope to continue to build and develop the software. One of my colleagues is in the process of comparing this package to some of the off-the-shelf packages. So I'm not clear exactly how that's going to come out, but we hope to develop some papers doing the comparison. And yeah, I do hope to continue to work, potentially even try to develop it. You know, right now it's based in SAS. Potentially it could be developed in other programming languages as well.
Yeah, great. Well, thank you very much. It's all exciting news, and we, if you can send us updates, we'd be happy to add that to the
Uh,
website as well.
well, I really appreciate you having me here.
Yeah.
And well, I do see for the contact information, you definitely, if people have questions, they want to contact me, the email address is going to be the most effective. The phone number is still operational, but since I haven't been in the office recently, you'd have to wait until I actually play the recording. But feel free to drop me a line
Yeah.
at the email address if you want to discuss any of these the points that I brought up in this talk,
Great.
or other questions about record linkage.
Wonderful. Well, thanks so much, Dean, and thanks everyone for joining us. You can look forward to the recording, and I'll send you all an email when it's up. All right. Bye for now.
Okay.